Hello everyone, I am Anika Priyatham, 11th grade aerospace researcher from National Public School, Whitefield, India, with an obsession for turning wild what ifs into physics backed engineering. Today, I want to take you 11 kilometers above sea level to cruise altitude, where most people imagine nothing but empty blue sky. But when I look at an aircraft slicing through that air, I don't see emptiness, I see an enormous unused energy field. And that led me to one question that changed everything for this project. What if an airplane didn't just consume energy? What if it generated it while flying? And that question became the foundation for my study on the aeroelastic integration of ultra thin photovoltaic and lead free piezoelectric nanostructures for high efficiency energy harvesting in aircraft services. Aviation produces about 2.5% of global anthropogenic CO2 emissions, and with air travel increasing faster than efficiency improvements, that number is projected to triple by 2050. The problem is that traditional aerodynamic refinements and engine cycle improvements are reaching diminishing returns. The easy gains are already taken. To go further, we need ideas that don't just tweak existing systems, but rethink them entirely. And it turns out that aircraft operating at cruise altitude are constantly interacting with two massive, free, and mostly untapped energy sources: solar irradiance, which can reach nearly 800 watts per meter square with no cloud obstruction, and aeroelastic vibrations, which are the high frequency oscillations introduced by turbulence and airflow over the wings. Every flight produces both, yet we harvest neither. My project asks, why not extract that energy directly from the aircraft's own surfaces? The heart of my idea is straightforward in principle but deep in engineering. I integrated two ultra thin energy harvesting materials into the aircraft wing surface itself. The first is a 1 to 3 micrometer perovskite based photovoltaic film, operating at 20% efficiency, and is thin enough to maintain the aerodynamic cleanliness of the wing. The second is a 100 nanometer barium titanate piezoelectric nanostructure layer, tuned to respond to vibration frequencies around 120 Hz, which is typical for cruise level aeroelastic oscillations. And instead of mounting anything on top of the wing, these layers are built into it. So the wing doesn't just retain its structural and aerodynamic properties, it becomes an active generator. Together, the PV and piezo layers form a multifunctional skin capable of harvesting solar energy and converting vibrational energy into electrical output, all while preserving aerodynamic performance. For the photovoltaic layer, I chose ultra thin perovskite films because they strike a rare balance between high power to weight ratio, flexibility, and aerodynamic friendliness. At just 1 to 3 micrometers, these films are roughly 50 times thinner than a human hair, which allows them to conform flawlessly to the wing surface without disrupting airflow. Their low thickness minimizes changes in surface roughness, which is a critical factor because even subtle roughness can prematurely trigger turbulence. The piezoelectric layer uses barium titanate based 100 nanometer films, chosen for being lead free, mechanically stable, and exhibiting strong piezoelectric coupling. At this nanoscale thickness, the piezo layer is essentially a functional coating, capable of converting wing vibrations, which are those tiny rapid oscillations produced as airflow flows over the surface, into electrical charge. For perspective, 100 nanometers is so thin that if the wing was scaled to the height of a skyscraper, the piezo layer would be like adding a single sheet of paper to it. These two materials, one harvesting light and the other harvesting motion, together form a hybrid multifunctional energy harvesting architecture. This project required a multi-physics approach because aerodynamics, structural vibrations, and electromechanical conversion all interact with each other. I began with CFD simulations, which allowed me to quantify changes in drag coefficient, examine boundary layer behavior, and locate the laminar turbulent transition. For clarity, the boundary layer is the ultra-thin region of air, just a few millimeters thick, that clings to the wing surface and determines how smoothly momentum transfers from the surface to the free flow. Laminar flow within this region is smooth, orderly, and low drag. Turbulent flow is chaotic and high drag. The exact point the exact point where airflow transitions from laminar to turbulent dramatically affects fuel consumption. So ensuring that the new surface layers didn't shift at transition points was essential. When you look at the laminar diagram here, the lines say smooth and straight, almost like calm water flowing past a rock. That's exactly what I needed to see. Even after adding my PV and piezo layer, the airflow didn't get disrupted, and the point where smooth flow normally turns turbulent didn't shift at all. But in the turbulent example on the right, you can see what would have happened if the layers had caused a problem. The lines get wavy, uneven, and start forming small swirls. Since my surface didn't cause those changes, it confirmed that the wing felt the same to the air, which is why the drag only increased by around 0.2%. Next, I used COMSOL multiphysics to model electromechanical coupling in the barium titanate layers and simulate photoelectric behavior in the PV films. I analyzed how efficiently the piezoelectric layers could harvest vibrational energy across the resonance center near 120 Hz, a typical frequency for cruise-induced aeroelastic vibration. COMSOL allowed me to simulate charge generation, mechanical stress distribution, and electrical output under dynamic loading, essentially letting me stress test the nanostructures without a lab. This strain map shows how the wing bends under load. The brighter colors near the root are completely normal. That part of the wing always carries the most stress. The important part is the coloring stays smooth everywhere else. If my layers had caused any issues, you see sharp jumps or bright spots in random places. But because everything bends gradually, it tells me the layers bend along with the wing naturally. That matches the numerical result too. The total mass went up by only about 0.054%, which is so tiny that the structure basically behaves the same as before. Finally, I integrated the modified wing geometry into Explain to evaluate system level performance, comparing energy generation, propulsive power demand, drag penalty, and structural mass increase against a baseline wing. This gave me a flight ready digital prototype with realistic in flight behavior. This plot shows how the drag changed at different speeds in the simulator. The black curve has a slight U shape, but what matters is how close it stays to the flat dashed line at 0.2%, which is the drag penalty I predicted from CFD. Even when the speed drops to about 0.6 or rises to 1.0, the drag only changes by a tiny amount. It stays within roughly 0.2 to 0.215%. That consistency shows that the modified wing behaves almost exactly as predicted, with no unexpected drag spikes and no aerodynamic penalties emerging at different speeds. The most exciting outcome is a net cruise power output of 192.39 kilowatts. To break that down, approximately 192 kilowatts come from the photovoltaic layer. It performs extremely well under cruise level irradiance, and about 390 watts come from the piezoelectric harvesting. While the piezoelectric contribution is comparatively small, its importance lies in being continuous, vibration driven energy production that works even when sunlight fluctuates. The drag penalty is remarkably low, of just about a 0.2% increase. In aerodynamic terms, that's almost negligible, comparable to adding an ultra thin coat of paint. If the drag penalty had crossed even 1%, the system would have lost more energy through fuel burn than it generated. Instead, the aerodynamics remain nearly identical to the baseline wing. Structurally, the mass increase is only 0.054%, equivalent to adding just a few textbooks to a commercial wing. This confirms that the ultra-thin material selection achieved its purpose, meaningful energy harvesting at almost no structural cost. Interpreting these numbers, the hybrid surface yields 2.56 times more energy than the cruise propulsion requirement of 75 kilowatts for the test configuration. This means that not only could the swing power itself, it could produce surplus energy for onboard systems, APUs, or future hybrid electric propulsion system. These performance outcomes open up several major possibilities. First, aircraft could significantly reduce their reliance on the APU, that is, the auxiliary power unit, which is responsible for powering essential onboard systems and can consume large amount of fuels, especially on long flights. Second, secondary electrical systems like avionics, cabin system, anti-ice systems, and environmental control could be partially or fully powered by the wing itself. Third, this energy harvesting approach lays the groundwork for hybrid electric propulsion architectures, where excess harvested power could assist propulsion or charge in-flight energy storage. And finally, the extremely small aerodynamic and structural penalties mean that we could scale this approach from narrow-body aircraft to wide-body platforms, where the available surface area multiplies. With wide-body wings, the system could generate megawatt-class power, enough to meaningfully offset fuel consumption in long-haul aviation. And this is not a future concept, it is a viable architecture backed by physics and simulation. The success of the system relies on three principles. First, solar irradiance at cruise altitude is exceptionally strong and consistent because aircraft fly above most atmospheric disturbances. Second, ultra-thin flexible materials minimize aerodynamic disruption because they integrate into the wing rather than sitting on top of it. Even microscopic changes to the surface geometry can impact drag, so the nanoscale thickness here is crucial. Third, aeroelastic vibrations produce a steady, always on mechanical energy source. Wings naturally oscillate thousands of times per minute due to airflow. Instead of viewing these vibrations as noise or structural fatigue contributors, the piezoelectric layers use them as fuel. In effect, the aircraft becomes its own generator, harvesting energy from both the environment and its own aeroelastic behavior. Even with promising results, scaling this technology requires solving several engineering challenges, and each challenge already has a realistic pathway forward. First, large area fabrication of ultra-thin PV and piezo layers is still complex, but techniques like roll-to-roll deposition, spray-on perovskites, and atomic layer deposition for piezoelectric nanostructures are rapidly maturing. These emerging methods could allow automated uniform coating of entire wing surfaces. A major focus of future work is optimizing these deposition methods for curved aerodynamic geometries. Second, environmental durability. UV exposure, rapid thermal cycling, and shear forces at high Reynolds numbers could degrade thin films. A solution here is embedding the layers under transparent polyurethane or fluoropolymer topcoats, similar to those already used on UAV solar wings. These coatings provide UV shielding and erosion protection without compromising flexibility or optical transmission. Long-term accelerated aging tests should be part of phase 2 validation. Third, thermomechanical coupling under high-speed aerodynamic loads need deeper studies. Realistically, this means expanding our COMSOL simulations to include fluid structure interaction models and then validating them in a subscale wind tunnel. Early modeling already suggests that stresses remain within safe limits, but experimental data will make the system certification ready. The roadmap ahead turns these solutions into a structured path forward deployment. The first step is fabricating a 30 to 50 centimeter test section so we can validate material behavior and power output on a representative curved aerodynamic surface. With that in place, the next phase is a controlled wind tunnel campaign, this time with turbulence management to benchmark performance across realistic flow regimes. After wind tunnel validation, the system moves to flight testing on a small UAV where we can study vibration coupling, real-time power harvesting, and durability under actual mission profiles. And finally, the long-term goal is scaling the architecture to a commercial wing prototype, an engineering milestone that will allow us to assess manufacturability, system integration, and true operation viability at scale. To close, this project shows that aircraft surfaces don't have to be passive. They can be active power generators, turning sunlight and aeroelastic vibrations into real usable electrical energy with almost no aerodynamic or structural penalty. With ultra-thin photovoltaic films and nanoscale barium titanate layers integrated directly into the wing, we're not just nudging aerospace towards sustainability, we're rewiring the entire relationship between an aircraft and its environment. This isn't just an incremental improvement, it's the start of a fundamentally new design philosophy. Aircraft that power themselves, aircraft that give back more energy than they take, aircraft that push us closer to true carbon neutral flight. And the best part? The physics work, the numbers work, and the engineering pathway is right in front of us. Thank you. I am Anika, and I generally believe that this kind of multifunctional aerospace design is how we can and will unlock the next generation of aviation.